Graph Theory Class 3 Video 1. In this video we're going to talk about an old famous problem called the Bridges of Konigsburg. This problem is often pointed to as the birth of modern graph theory. It's a very important and famous problem, and it inspired a lot of what is now considered graph theory. But let's talk about it in the original historical context. So, some history first of all. Konigsburg was a Prussian city a long time ago. It now goes by the name Kaliningrad, and it's part of Russia. For some reason, a strangely high proportion of academic famous people were born in Konigsburg, like Christian Goldbach from the Goldbach conjecture, Immanuel Kant, the philosopher, and David Hilbert, the mathematician. They were all born in Konigsburg, or Kaliningrad as it's now known. But what's relevant for us is the fact that there is a river that runs through the city. There are 4 land masses, and there are 7 bridges. Okay, and I'll show you a picture in a minute. But the challenge, like a popular challenge back in the day, a long time ago, was to try and cross every bridge exactly once. So years ago, when people were bored in Konigsburg, they would go for a walk and they would try and cross every bridge exactly once. And this is a rough map of the bridges of Konigsburg. Okay, so the yellow bits are the bridges, the blue bit is water, and the other bits are land. So this is land, this is land, land, land. They're the 4 land masses. So the problem was, back in the day, can you cross every bridge exactly once? Yeah, and that's it. You don't even need to return back to where you start. You just need to cross every bridge exactly once. So you can start anywhere, and you can finish anywhere. Doesn't need to be in the same spot. The question is just, can you cross every bridge exactly once? So for many, many years, a lot of people would just try and walk about crossing these bridges and failing. There was a lot of failing to do this challenge. So you can just try it, right? Like, you can go across this bridge, across this bridge, this bridge, this bridge, this bridge, this bridge. But now I've missed a bridge, so that doesn't work, right? Maybe if I start somewhere else. So I can start here. I can go like this. And now I've missed this bridge. So that doesn't work either. Okay? And I recommend that you pause this video and try and solve this puzzle by yourself. Okay? It's a lot easier to think about when you have this map, right? You can just try and doodle on a piece of paper and try and solve this problem for yourself. Okay, so now I'll tell you a theorem. It's actually impossible to do this. It's impossible to walk across all 7 of the bridges exactly once. Okay? No matter what clever sort of path you try to come up with, it will never work. It's impossible to do this. Okay? And this was first proven by someone called Euler. Okay, so he's a very famous mathematician, and he heard about this problem from afar, and he was the first person to give any sort of proof that it's impossible. Okay, and people sort of point to this problem, Euler's proof of the impossibility of crossing all 7 bridges, as the birth of graph theory. The ideas which he uses are sort of central to a lot of modern day graph theory. So let's do this proof. Let's prove that it's impossible to cross all 7 bridges exactly once. So I'm going to redraw the map here, okay? And the first thing I'm going to do is I'm going to say, well, if I'm going to talk about paths like this, I want like an algebraic way of writing down a possible path. So what I'm going to do is I'm going to label the land masses. So I'm going to call this A, this B, this C, and this D. So the land at the top is called A, the land to the right is called B, to the south is called C, and the island is called D. And now I'm going to label the bridges as well. So I'll call this bridge lowercase a. This is lowercase b, c, d, e, f, g. Okay, so I've labeled the land masses and the bridges. Okay, and I did this because now a walk, I can sort of encode a walk like follows. So a walk could look something like A, D, E, C, D, B. And what does this mean? It means I start at A, I cross the bridge labelled lowercase a, and then I'm in D. I cross the bridge labelled lowercase e, and now I'm in C. I cross the bridge labelled lowercase d, and now I'm in B. That's what this means. This algebraic sequence of letters corresponds to this walk on the map. Okay? So, if it was possible to have a walk which crossed every bridge, all 7 bridges exactly once, then that would look like it would have a certain form. It would have a certain structure algebraically. So, if I say, assume it is possible to cross all 7 bridges exactly once. Okay, then what would that walk look like? Well, I don't know exactly, but I know it would be a combination. It would have to be like an uppercase letter, then a lowercase letter, then uppercase, then lowercase. Okay, so these boxes, I don't know what goes in them, but I know it has to be uppercase, lowercase, uppercase, lowercase. And how many lowercase letters do I need? Well, there are 7 bridges, so that means I need 7 small boxes. 1, 2, 3, 4, 5, 6, 7. Okay? Like, I don't know exactly what goes in these boxes, but I know that it has to be, the big box is uppercase, and the smaller box is lowercase. Okay, so I'm assuming that it is possible to cross all 7 bridges once, and what I'm going to do now is arrive at some sort of contradiction. So assuming that such a walk exists, I'm going to show that that leads to something impossible. So that means my assumption had to be false in the first place. Okay, so if such a walk exists, I'm going to ask the question, how many times do I need to stand on landmass A? Okay, so if I have this walk which crosses all the bridges exactly once, what's the minimum number of times I need to stand on A? Well, I can think about it like this. I need to cross this bridge, and this bridge. Okay, and I could end up doing something like this and this, and I don't know what happens elsewhere, but notice that this means that I need to stand on A at least 2 times. I need to stand on the landmass capital A at least 1 time, and then another time. Okay, so I'm going to write this down. So A must occur at least 2 times. Right, I need to stand on A at least 2 times, which means that in this big list, in this hypothetical walk here, I have to have A capital A at least 2 times. I don't know where. Like it could be here and here, or it could be like here and here for all I know. I don't know where it goes. All I know is that it has to be there at least twice. Okay, now I'm going to do the same thing with B. So how many times do I need to stand on B? Well, the same sort of argument. There are 3 bridges leading to B. Okay, and I could do something like that, which gets rid of 2 of the bridges, and I stood on B 1 time, and then I need to stand on B another time to get the 3rd remaining bridge. So I need to stand on B at least 2 times. So B must occur at least 2 times. Now do C. How many times does C have to occur? Well, C is very symmetric with A, if you think about it, right? Like I could do something like that and this. So at least 2 times. There's no way I can get all 3 of these bridges and only step foot on C once. That's just not possible, right? Because if you think about it, at best you cross off a bridge when you go into C, and then you cross off a different bridge when you leave C. So that means every time you step on C, you can use at most 2 bridges. Well, I have 3 bridges, so that means I need to step on C at least 2 times. Okay, so C must occur at least 2 times. And finally, let's do D. So how many times does D have to occur? Well, D has 5 bridges. So I could maybe do that, and then that one. So it's 3 times. I need to step on D at least 3 times in order to cover all 5 of those bridges. So D must occur at least 3 times. Okay, and same as before, I don't know exactly where D is going to occur. Like it could be here, here, and here. It doesn't matter. It's just I know that there has to be at least 3 D's in this word up here, in this box word. But now the contradiction comes when you add up all of these occurrences. So 2 plus 2 plus 2 plus 3. That's 6 plus 3 is 9. So I have to have 9 uppercase letters. Okay? But if you count how many boxes I have, how many big boxes, 1, 2, 3, 4, 5, 6, 7, 8. I only have 8 big boxes. But we only have 8 big boxes. Okay? This is a contradiction. Right? I said if such a walk exists, then it has to look like this. Okay? But then I also worked out that such a walk has to have at least 9 uppercase letters. And there's just not enough room to put 9 uppercase letters in here. So that means that's a contradiction. So no such walk exists. Okay, and that's the end of the proof that it's impossible to cross all 7 bridges of Konigsburg. And like I said before, this proof, it's sort of the birth of graph theory. So in subsequent videos, we're going to look at how we can translate this problem into a more modern graph theory language. But that's the end of this video.